Welcome back to Very Ordinary Differential Equations. In this lecture, we continue our study of non-homogeneous second-order linear equations with constant coefficients. Now, having already studied how to deal with an exponential forcing function or a trigonometric forcing function, we combine it to a product of the two. So we're going to combine the previous two topics. We now wish to solve a general second-order linear differential equation with constant coefficients, but our forcing function is made up of exponentials times trigonometric functions. So we have a forcing function that can be expressed as a product of exponential and trigonometric terms. If there was a mixture of different exponents or different periods or different phase shifts, the superposition principle would allow us to treat them separately. Here I want to point out that the exponents on these two terms are the same, and the period and phase shift of our trigonometric terms is also the same. Now, unsurprisingly, to find some particular solution, we really need to determine if the forcing function is or is not a solution to the complementary equation. And then we can use one of two different techniques according to whether it isn't a solution to the complementary equation or it is. Now, in trying to solve this differential equation, we're going to start off with a few simplifications. The phase shift can be assumed to be 0. Whatever phase shift you put in your sine or cosine terms will not change under differentiation, so you can kind of ignore it and reintroduce it at the end if necessary. We're also going to assume that we have either a sine or a cosine function, rather than trying to treat both at once. If you happened to have both, well then the superposition principle can still be used to do each term individually. Then we're going to assume that the scalar k1 or k2 is just 1. Okay. Rather than deal with a linear combination of these two terms to begin with, we're going to ignore one of them altogether and assume that the other coefficient is 1. Then, through a combination of linearity and the superposition principle, we could recreate anything we wanted. So let's just try to solve ay double prime plus by prime plus cy is e to the lambda x times the sine of omega x. We've kind of ignored the phase shift, we've ignored the possibility of a cosine term, and whatever the multiple out in front is, we've assumed it's just 1. So we're going to set y sub p to take on a similar form. But since there are two derivatives present, we're going to end up with this mixture of sines and cosines. So our proposed forcing function should have the same exponent, and the sine and cosine should have the same period as our desired sine function, but we will need some combination of sines and cosines. Now we compute yp prime and yp double prime. Takes a little bit of care. Okay, we have to apply all the product and chain rules as we go, but ultimately, here is the first derivative, and here is the second derivative. So we've got our differential equation, our proposed solution, its first derivative, and its second derivative. So what we now need to do is take yp double prime, plug it in here, yp prime, plug it in here, yp, substitute it in there, and see what conditions on all of our unknowns arise in order to make the result exactly that term. So ayp double prime plus byp prime plus cyp is just e to the lambda x and then something times a sine and something times a cosine. You can see quite directly if I take this and multiply it by little a, and this and multiply it by little b, and this and multiply it by c, everything's got an e to the lambda x that I can factor out. Then I've got a bunch of sines and cosines. So ultimately, we're going to group all the sines together and all the cosines together. The multiple in front of the sine turns out to be this right here, and the multiple in front of the cosine is this expression right there. So now what do we want? We want big X to be 1 and big Y to be 0, because ultimately we wanted to have one of these sines and no of these cosines. So where are we? We want all of this to be 1 and all of this to be 0. Everything in here is known except for capital A and capital B. So since we're trying to solve for capital A and capital B, we're going to factor capital A or capital B out of everything we can. So in the first and second equation respectively, if I group according to whether the term has capital A or capital B, here's what we end up with. So now what we want is all of this, which is multiplying capital A, to be alpha, and all of this to be beta, Then the top equation turns out to be A alpha minus B beta, and we want that to be 1. Whereas the second equation actually is A beta. Notice that this is the same as that up to a minus sign. That's why we have the minus sign right there. And this is exactly the same as that. So now I have, after all of this reworking, a rather simple looking system of two equations and two unknowns. Alpha and beta are expressible in terms of all of the known quantities. In our original differential equation, little a, little b, and little c were coefficients. Omega was related to the period of the resulting sine function, and lambda was the exponent on the exponential term. So we can compute alpha and beta, and now we have this nice little system. So ultimately, once we set alpha to be this expression, beta to be this expression, we have this system of two equations and two unknowns, and we need to solve for capital A and capital B. And it's not terribly difficult to work through the solution, and here they are. So capital A should be alpha over alpha squared plus beta squared, and capital B should be negative beta over alpha squared plus beta squared. Of course, this does require that that denominator not be 0. So we have a somewhat lengthy but just tedious computation that gives us alpha, and another computation that gives us beta. Then, if we wanted to solve ay double prime plus by prime plus cy equals e to the lambda x times the sine of omega x, we derived a nice explicit formula for what particular function we should use. However, it involved constants capital A and capital B that themselves required division by alpha squared plus beta squared. Therefore, alpha squared plus beta squared can't be 0 for all of our previous work to be valid. But what if alpha squared plus beta squared is equal to 0? Now, the only way the sum of two squares can possibly be 0 is if both things individually are 0. Now, beta is computed up here. The only way all of this can be 0, well, I can cancel an omega out because omega definitely isn't 0, or I wouldn't have had a forcing function. Okay, so I can cancel out omega and derive that 2a lambda plus b must equal 0. In other words, 2a lambda equals negative b, and if I solve that for lambda, we get lambda is negative b over 2a. But how can alpha equal 0? Well, alpha was computed through all of this. So if alpha is 0 and I move the a omega squared to the other side, we end up with a omega squared equals a lambda squared plus b lambda plus c. But how can they both be 0? I'd have to have both of these conditions. So both of them are 0. Well, lambda is now specifically replaced with negative b over 2a. So if I replace lambda with negative b over 2a in both positions here, okay, it will be derivable. We're kind of glossing over the work. However, the characteristic polynomial, which is right here, okay, is exactly going to have roots lambda plus or minus omega I. So what's the situation so far? We have a second order linear differential equation with constant coefficients, and we want to produce a very specific forcing function, e to the lambda x sine of omega x. Provided that e to the lambda x sine omega x does not solve the characteristic equation, in other words, lambda plus or minus omega I are not the roots of the characteristic polynomial, well then, the alpha and beta that we would have computed in our other technique will not both be 0. In other words, I can simply set y sub p to be this expression right here, where capital A and capital B are computed in terms of alpha and beta. And alpha and beta are computed through these formulas right here. And under the assumption that lambda plus or minus omega I are not roots of this polynomial, it will happen that alpha and beta are not both 0. In other words, I can divide by alpha squared plus beta squared, and everything checks out here. Well, what if we have the same equation, ay double prime plus by prime plus cy, and now we want to produce a forcing function e to the lambda x cosine omega x instead of sine? Very little changes. The solution is given by y sub p is e to the lambda x a sine omega x plus b cos omega x, just as it was before, but now a and b are computed slightly differently. However, alpha and beta are exactly the same things that they were before. So we just have a marginally different formula for how to compute these coefficients a and b, but essentially the work is all pretty much the same. But what if alpha squared plus beta squared is equal to 0? As we've discussed, alpha squared plus beta squared can equal 0 if and only if alpha and beta are both equal to 0, if and only if lambda plus or minus omega I are exactly the roots of the characteristic equation. Now the characteristic equation, remember, is this second degree polynomial created from the differential equation. If I know exactly two roots of a second degree polynomial, then I know exactly what polynomial that is. Okay, it would be r minus lambda plus omega I and r minus lambda minus omega I, which I could then re-expand and determine exactly what differential equation created that characteristic polynomial. And it would be exactly this one, y double prime minus 2 lambda y prime plus lambda squared plus omega squared y equals 0. So this is the possible bad scenario. Okay, when I want to create a forcing function of e to the lambda x sine or cosine of omega x, and our differential equation is exactly this. Now this really overlaps with previous work to a great extent. When the forcing function was purely exponential, just e to the lambda x, you can imagine that as being e to the lambda x times the cosine of 0, because the cosine of 0 is 1. And omega equals 0 simplifies this polynomial a good amount. Now, when the forcing function was purely sinusoidal, you can imagine that as being lambda is 0, because then e to the lambda x would just be 1. And if lambda is 0, this equation simplifies a good deal. At this point, we're going to do a bunch of work that's similar to things we've done before. We have a differential equation with a proposed forcing function, but of a very, very specific form. The form actually guarantees that the forcing function we want to produce solves the complementary equation. So what do? We take what we would have done, exponential sine and exponential cosine, but we multiply an extra x across. Then what we're going to have to do is compute yp prime, yp double prime, throw them into the differential equation, group all the terms we get according to whether we have an e to the lambda x sine x or an e to the lambda x cosine term. Then everything multiplying the proposed sine term should be set equal to 1 because our forcing function is to have one of those sine terms. And everything multiplying e to the lambda x cosine omega x, that factor should be set equal to 0. We just need to solve for the capital A and capital B that will make all of that happen. So skipping over some work, okay, here is the differential equation with the forcing function we're trying to solve and our proposed solution. Once we compute yp prime, yp double prime, and throw it into the differential equation and then group according to whether we have e to the lambda x sine omega x or e to the lambda x cos omega x, here's what you would get. Okay, there's a whole lot of simplification, but it just boils down to this. Okay, there's a lot of simplification that happens, which is really amazing and great. E to the lambda x times negative 2b omega sine omega x plus 2a omega cosine omega x. So after all of this simplification, we have our proposed solution, we threw it into the differential equation, and we ended up with something that wasn't really that bad. Now, since we want the result to be e to the lambda x sine omega x and 0 e to the lambda x cos omega x's, this tells me that b should be negative 1 over 2 omega, then I will have exactly one of these, and a should be 0, and then this will go away. That turns my proposed solution into something pretty straightforward. Negative 1 over 2 omega times x e to the lambda x cosine omega x. And if the forcing function I were trying to get out was e to the lambda x cosine omega x, well then, I would want this to be 1, so I would set a to be 1 over 2 omega, and I'd want this to be 0, so I would set b equal to 0. That would turn the proposed solution into positive 1 over 2 omega x e to the lambda x sine omega x. So according to whether you want to get out e to the lambda x sine omega x or e to the lambda x cos omega x, here are the y sub p's that do that. And again, this is for the very specific differential equation where e to the lambda x sine or cosine omega x are solutions to the complementary equation where that's all set equal to 0. With all of those formulas derived and behind us, we can apply them to solving some problems. Let's find a single solution yp which solves y double prime minus 2y prime plus 3y equals e to the 5x times the sine of 2x plus 3. The phase shift, that plus 3, really not a big deal. We'll just add that back in at the end. What we really care about is whether the forcing function is or isn't a solution to the complementary equation, because that will determine which formula we use. Now, the complementary polynomial is r squared minus 2r plus 3. The quadratic formula gives us that r must be 2 plus or minus the square root of negative 8 over 2. In other words, the roots of the complementary polynomial are 1 plus or minus root 2 times I. So a fundamental set of solutions is given by e to the x times the sine or the cosine of root 2 times x. So our forcing function is just not a solution to the complementary equation, so we can use our first formula. So the first formula said, if I want to solve ay double prime plus by prime plus cy equals e to the lambda x times the sine of omega x plus phi, we use yp equals e to the lambda x, which is 5, times a times the sine of omega x plus phi plus b times the cosine of omega x plus phi, and we know what omega and phi are. All we have to do is solve for capital A and capital B, where capital A and capital B were computed as quite explicit formulas. Alpha over alpha squared plus beta squared and negative beta over alpha squared plus beta squared, respectively, where alpha and beta themselves had explicit computations to derive them. So we just have to match term by term what we have here. A, the coefficient on y double prime, is 1. B, the coefficient on y prime, is negative 2. C, the coefficient on y, is 3. As we've already mentioned, lambda is 5 and omega is 2. And that allows us to compute alpha and beta. And once we've computed alpha and beta, we can compute capital A and capital B. So alpha is 14 and beta is 16. Which makes capital A 14 over 452 and capital B negative 16 over 452. And now that I know capital A and capital B, I simply take those back up here to get my particular solution. Okay, so with our particular solution being only in terms of capital A and capital B, which we've now computed, I can say that our particular solution is e to the 5x times 14 over 452 times the sine of 2x plus 3 minus 16 over 452 times the cosine of 2x plus 3. And yeah, those fractions can probably be simplified. I mean, they definitely can. But that's not really a big deal, and it's not really the interesting part of this problem. As a second example, let's find a single solution to y double prime minus 2y prime plus 3y equals e to the x cosine of root 2x plus 3. Well, notice I did not change the left side there, y double prime minus 2y prime plus 3y. Okay, so we've already found a fundamental set of solutions, and indeed, e to the x cosine of root 2x was in there. So our forcing function is a solution to the complementary equation, which means we're going to use our alternate formula, where yp is 1 over 2 omega x e to the lambda x sine omega x. That was to produce e to the lambda x cosine omega x plus phi when this is a solution to the complementary equation. All we have to do is identify that omega is root 2 and lambda is 1. And don't forget to re-add the phase shift. Okay, this formula that we derived didn't have a phase shift plus phi. Honestly, it just made the equation longer and not quite fit on the page. But adding that phase shift in does not change anything about differentiation, so nothing really changes in finding particular solutions to differential equations. So substituting omega is root 2 and lambda equals 1, and re-adding that phase shift to plus 3, here is our particular solution. And a third example. Let's do an initial value problem. Y double prime minus 2y prime plus 2y equals e to the x sine x plus e to the x cosine of 2x, where y of 0 is 0 and y prime of 0 is 1. Well, we've got to find general solutions to this equation, which first requires finding general solutions to the complementary equation. So first, let's set the forcing function to be 0 and see what's what. So we've got to find the roots of the characteristic polynomial, r squared minus 2r plus 2 equals 0, which are given by 1 plus or minus I. Okay, the quadratic formula will spit this out for you quite directly. So a fundamental set of solutions is given by e to the x times the sine or cosine of x. Now we have two forcing functions. E to the x sine x does solve the complementary equation, and e to the x cosine of 2x does not. While the exponential term is the same, since the cosine function has a different period, it's fundamentally a different function. Okay, so of our two forcing functions, This one here does solve the complementary equation. This one does not. So we need to find two different functions yp and yq, so that yp will produce e to the x cos x and yq will produce e to the x cosine of 2x. Now the first forcing function does solve the complementary equation, so therefore we use this formula right here. Yp should be 1 over 2 omega x e to the lambda x sine omega x, which simplifies down to just 1/2 x e to the x sine x, since lambda and omega are both 1. Now we can try to find a yq, so that yq double prime minus 2yq prime plus 2yq equals e to the x times the cosine of 2x. Since this doesn't solve the complementary equation, we use our other formula and we set yq to be e to the lambda x a sine omega x plus b cos omega x, where capital A and capital B are explicitly computed as such, where alpha and beta were explicitly computed as such. And we simply read out that a is 1, b is minus 2, c is positive 2, omega in this case is 2, and lambda is still 1. And now I can compute alpha and beta, therefore capital A and capital B. So alpha is 3, beta is 0. With alpha being 3 and beta being 0, we can plug this in and get capital A is negative 1/3 and B is 0. Therefore, y sub q, with a being negative 1/3 and b being 0, would reduce to just negative 1/3 e to the x times the sine of 2x. So we know a fundamental set of solutions to the complementary equation, and we found two particular solutions to give each of the individual components of the forcing function, yp and yq. Therefore, a general solution to our differential equation must be given by some linear combination of the fundamental set of solutions plus the two particular solutions we found. We can take a derivative of this. So here was our general solution. On the previous slide, we computed a derivative of it. It will be coming back shortly, don't worry. We just need to use our initial values. First, y of 0 is 0. Well, if I plug in x equals 0 and y equals 0, a lot of stuff vanishes. All of our sine terms, for example, vanish, and the cosine of 0 is 1. So we directly get that c2 had better equal 0. Here was what we computed to be the derivative, y prime. And if y prime of 0 is 1, well then, c1 plus c2 minus 2/3 is equal to 1. Again, letting x equal to 0 is going to make all of our sine terms vanish. And since c2 is 0, this reduces to c1 being 5/3. So here was our general form for a solution, but with our initial values, we determined that c2 is 0 and c1 is 5/3, so we know exactly what function solves our initial value problem. Y is 5/3 e to the x sine x plus 1/2 x e to the x sine x minus 1/3 e to the x sine 2x. Overall then, what have we covered? If we have a second-order linear differential equation with constant coefficients, if we have a forcing function that is some product of an exponential and trigonometric function, we now have some very general formulas that tell us what to do. But what's always important is to determine, is the forcing function I'm looking at a solution to the complementary equation or not? If it is or isn't a solution to the complementary equation, that will drastically change what formulas are important. So don't just stare at a formula on some page somewhere and start computing stuff before you know if that's actually a formula that helps you. Some of the formulas we derived presumed that the leading coefficient, the term in front of y double prime, was 1. Others didn't, so sometimes we needed y double prime with a 1 in front. Other times it was allowed to be a y double prime where a was arbitrary. So again, before blindly using a formula on a page, make sure that it matches the format that you need. Also, everything we did here, if you set lambda equal to 0, well then your forcing functions have e to the 0, in other words a 1, and then your forcing functions just go back to being sines or cosines. If, however, I set omega to be 0, then this would vanish altogether because the sine of 0 is 0, but the cosine of 0 is 1, and I would recover just exponential terms. So the material of this section can completely replace all the material we did for purely exponential or purely trigonometric forcing functions. However, I wouldn't necessarily recommend you just throw all that stuff out. The formulas in this section were a bit more complicated to use, and therefore it's just more likely you're gonna make a computational error. You're accidentally gonna compute 2 times 3 equals 5, or you're gonna push a 7 on your calculator when you meant to push a 6. Okay, the longer and more complicated the formula is, the more likely it is you'll just make a boneheaded mistake when trying to use it. So I wouldn't say totally throw out the old material. It's a little easier to use when it applies. What I'm really trying to point out here is to say that all of the formulas we derived here are in fact consistent with the ones we've already derived. When lambda equals 0, you go right to the trigonometric scenario, and when omega is 0, you go right to the exponential scenario.